At the very center of the Milky Way, buried behind layers of dust, gas, and crowded stars, there is something we cannot see with our eyes. No telescope, no matter how powerful, can look at it directly in visible light. And yet, everything in our galaxy knows it is there. Stars orbit faster as they draw closer. Gas clouds stretch and twist. Space itself curves inward. Hidden in the direction of the constellation Sagittarius lies an object so massive that it quietly anchors the entire Milky Way. This unseen presence is known as Sagittarius A star, a supermassive black hole with the mass of millions of suns, resting at the heart of our galaxy. For most of human history, the center of the Milky Way was not a place of certainty, but of confusion. When ancient observers looked up at the night sky, they saw a glowing band stretching from horizon to horizon, a pale river of light made from countless distant stars. That band appeared brightest toward one particular region, thick with light, but also streaked with darkness. From Earth, it was impossible to tell whether that glow marked a true center or simply a dense patch of stars. Dust clouds blocked the view, scattering visible light and hiding whatever lay beyond. To early astronomers, the galaxy seemed symmetrical, calm, and evenly spread. The idea that something extreme sat at its core was not obvious at all. Even as telescopes improved, the illusion persisted. Optical instruments could resolve individual stars, nebulae, and clusters, but when they turned toward the galactic center, they encountered a wall. Not an absence of stars, but too many of them, layered on top of each other and veiled by thick lanes of interstellar dust. The more powerful the telescope became, the more crowded and chaotic the view appeared. Light from the true center never reached Earth in a clean form. The Milky Way kept its heart hidden behind its own structure. For a long time, this led to a simple misunderstanding. Astronomers assumed that because stars appeared evenly distributed across the sky, the sun must lie somewhere near the galaxy's center. Only later did it become clear that this apparent balance was an illusion created by dust and distance. The real center lay far away, roughly 26,000 light-years from Earth, in a direction we could not see through. The galaxy did have a heart after all, but it was buried deep beneath layers of obscuring material. What makes this hidden center remarkable is not just its location, but its nature. Sagittarius A star is not a star in any traditional sense. It produces no light of its own. It does not shine or burn or radiate warmth like the sun. Instead, it bends the universe around it. Its gravity is so strong that stars near it move at thousands of kilometers per second. Some complete full orbits in just a few decades, tracing invisible paths around something they never touch and never see. From their motion alone, astronomers realized that only one type of object could explain what was happening. At the center of the Milky Way sits a black hole. Not a violent, raging one, blazing with jets and light across the cosmos, but a quiet giant. Sagittarius A star is relatively calm, feeding slowly, producing only faint flickers of radiation that occasionally escape its surroundings. Compared to the blazing cores of distant galaxies, it is subdued, almost restrained. Yet its calm should not be mistaken for weakness. Its mass is immense, roughly 4 million times that of our Sun, compressed into a region smaller than our solar system. Space and time behave differently in its presence. The closer you get, the more extreme reality becomes. What makes Sagittarius a star especially compelling is not only what it is, but how we came to know it exists at all. This black hole was not discovered by seeing it. It was discovered by listening, by tracing the faint whispers of radio waves passing through dust that visible light could never penetrate. Long before anyone could image its shadow, scientists detected its influence indirectly through distorted signals, strange motions, and subtle clues embedded in the behavior of stars and gas. Piece by piece, the picture emerged. This is the story of how humanity uncovered the hidden heart of its own galaxy. A journey that spans decades, technologies, and entirely new ways of observing the universe. It is a story about learning to see without light, about trusting gravity as evidence, and about understanding that some of the most powerful objects in the cosmos reveal themselves not through violence, but through patience. Sagittarius A star does not announce its presence. It waits, shaping the galaxy quietly from the inside, while stars, planets, and civilizations drift unknowingly around it. And as we begin to understand this silent monster at the center of the Milky Way, we are forced to confront a deeper realization: that our home galaxy, which feels vast and stable, is built around something profoundly extreme, something ancient, something invisible, something that reminds us that the universe does not need to be loud to be powerful. For centuries, the greatest obstacle to understanding the center of the Milky Way was not distance, but interference. Between Earth and the galactic core lies a vast amount of interstellar material. Clouds of microscopic dust grains drift through space, formed from the remnants of long-dead stars. Though individually tiny, these particles are spread across enormous distances, and together they are remarkably effective at blocking visible light. When starlight tries to pass through them, it is scattered and absorbed, leaving dark gaps and smudges across the sky. Nowhere is this effect stronger than in the direction of the galactic center. From Earth's perspective, the central region of the Milky Way is one of the most crowded parts of the sky. Hundreds of billions of stars are packed into a swollen bulge at the galaxy's core. Their combined light creates a bright haze, but mixed into that glow are thick lanes of darkness where dust obscures everything behind it. Early astronomers could see the foreground stars clearly, but anything deeper vanished into confusion. The signals were there, but they overlapped, blurred, and drowned each other out. The heart of the galaxy was hidden in plain sight. This created a strange paradox. The brightest region of the Milky Way was also the least understood. Telescopes grew larger. Mirrors became more precise. Yet the center remained stubbornly opaque. The problem was not resolution, but wavelength. Traditional telescopes were designed to collect the same kind of light our eyes evolved to see. That light simply could not pass through the dusty veil. To truly explore the galactic core, astronomers needed a different sense entirely. The breakthrough came when scientists began to realize that light is far more than what human vision can detect. Beyond the narrow band of visible colors lies a vast electromagnetic spectrum. Infrared light carries heat. Radio waves stretch across space with long, gentle oscillations. Unlike visible light, these longer wavelengths can slip through dust with far less interference. Where optical telescopes saw darkness, radio and infrared instruments could hear and feel what was hidden. The first hints arrived quietly and by accident. In the early 20th century, radio waves were not tools for astronomy. They were tools for communication. Engineers were trying to understand why radio signals sometimes crackled with unexplained noise. In the 1930s, while investigating sources of interference, a rotating antenna picked up a steady signal that repeated with the rhythm of the stars rather than the sun. Night after night, it returned from the same region of the sky. The source was not earthly. It was not solar. It was coming from deep space, from the direction of the Milky Way's densest region. At the time, no one was searching for black holes. The concept itself was still largely theoretical. But this unexpected signal marked the first moment humanity detected the galactic center using something other than light. The Milky Way had spoken in radio waves long before anyone knew how to listen. As radio astronomy developed, larger and more sensitive antennas began to map the sky. What emerged was a universe filled with invisible structure. Cold gas clouds glowed softly in radio frequencies. Supernova remnants traced ghostly shells across space. And near the center of the galaxy, one radio source stood out. Compact, persistent, unusually strong. It was labeled Sagittarius A, named simply for its position in the sky. Over time, instruments improved, and that single source was resolved into multiple components. One of them was smaller, denser, and far more intriguing than the rest. It appeared to come from an extremely confined region, far too compact to be a cluster of stars. This central source was given a distinctive name, Sagittarius A star. Not because it was a star, but because it marked something special, something excited, something different. Still, even radio waves could not reveal its true nature on their own. They could tell astronomers where it was and that it was powerful, but not what it was. To solve that mystery, scientists would need to watch how the galaxy itself responded to its presence. They would need to observe stars moving under its influence, tracing invisible paths through space, pulled by gravity alone. And to do that, they would need to see through the dust once again, this time with infrared eyes. Infrared light changed everything because it allowed astronomers to do something that had never been possible before. It allowed them to separate the foreground from the background. Dust that completely blocked visible light became almost transparent at longer wavelengths. Where optical telescopes saw confusion, infrared instruments began to reveal order. Individual stars emerged from the haze, not as a single glowing mass, but as distinct points moving through space. At first, these infrared observations were crude. Early detectors were noisy and imprecise, and Earth's atmosphere absorbed much of the infrared signal before it could reach the ground. To compensate, astronomers placed telescopes on high mountains, where the air was thinner and drier. Over time, infrared cameras became more sensitive, and new techniques were developed to cancel out atmospheric distortion. Slowly, the center of the Milky Way came into focus. What researchers found was not stillness, but motion. Near the position of Sagittarius A star, stars were moving far faster than anywhere else in the galaxy. These were not gentle, leisurely orbits like the Sun's path around the Milky Way. These stars were racing along tight paths, changing position noticeably over just a few years. Some traced elongated loops. Others swung in close, accelerated dramatically, then curved away again. It was immediately clear that something enormous was pulling on them. To measure these motions accurately, astronomers had to be patient. A single image meant nothing. Meaning only emerged when the same stars were tracked again and again. Year after year, their positions recorded with extreme precision. This kind of work demanded not only powerful telescopes, but consistency, persistence, and time itself as a measuring tool. Two independent teams took on this challenge. One observed from the deserts of Chile, the other from the volcanic peaks of Hawaii. Both used infrared telescopes equipped with adaptive optics, systems that corrected atmospheric turbulence in real time by reshaping mirrors hundreds of times per second. This allowed the stars near the galactic center to be seen with unprecedented clarity. As the data accumulated, the patterns became unmistakable. These stars were orbiting a common point, not a bright object, not a visible cluster, a point of darkness. One star in particular became famous. Known as S2, it follows an elongated orbit that brings it astonishingly close to Sagittarius A star before flinging it back out again. At its closest approach, S2 travels at thousands of kilometers per second, a significant fraction of the speed of light. No ordinary object could produce such extreme motion. By applying the laws of gravity, astronomers calculated the mass of whatever lay at the center. The result was extraordinary. More than 4 million times the mass of the Sun was packed into a region no larger than the orbit of Mercury. There was no light source there, no cluster of stars, no structure that could be resolved even with the sharpest instruments. The only object known to physics that fit these conditions was a supermassive black hole. This conclusion did not arrive suddenly. It emerged slowly, strengthened by each passing year of observation. As more stellar orbits were measured, they all pointed to the same invisible anchor. Their paths followed the predictions of Einstein's theory of general relativity, not just Newtonian gravity. Time itself appeared to run differently for stars passing close to the unseen center, exactly as relativity predicted in the presence of extreme mass. For the first time, a supermassive black hole was not inferred from distant explosions or energetic jets in other galaxies. It was revealed through calm, precise measurement. Through the quiet choreography of stars moving in darkness, Sagittarius A star was no longer a hypothesis. It was no longer a radio mystery or an infrared curiosity. It was a gravitational fact. And yet, even with this certainty, the black hole itself remained unseen. Astronomers had mapped its influence with astonishing accuracy, but the object at the center still refused to show its face. To see it directly would require something even more ambitious. A telescope the size of the Earth, a wavelength capable of slipping through dust and plasma, and a way to freeze motion in one of the most dynamic environments in the galaxy. Only then would humanity attempt to look directly into the shadow of the monster at the center of the Milky Way. A black hole is one of the simplest objects in the universe to describe, and one of the most difficult to truly understand. At its core, it is defined by a single idea: mass compressed into such a small volume that gravity overwhelms everything else. Once matter crosses a certain boundary, known as the event horizon, there is no path back out. Not for particles, not for light, not even for time itself, as we normally experience it. Sagittarius A star belongs to the largest known class of black holes, known as supermassive black holes. These objects are not formed from individual stars. No star, no matter how large, could collapse directly into something with millions of times the Sun's mass. Instead, supermassive black holes are thought to grow slowly over cosmic time, starting from smaller seeds and gaining mass by consuming gas, dust, and occasionally entire stars. Some may also grow through mergers, when galaxies collide and their central black holes spiral together into a single, larger object. What makes Sagittarius a star unusual is not its size, but its temperament. Many supermassive black holes are anything but quiet. In distant galaxies, some blaze with such intensity that they outshine all the stars around them, combined. These objects power quasars, producing vast disks of glowing matter and launching jets of energy that stretch thousands of light-years into space. Compared to those cosmic beacons, the black hole at the center of the Milky Way is subdued. It feeds slowly. It emits little radiation. Most of the time, it barely announces itself at all. This quiet behavior puzzled astronomers at first. The galactic center is crowded with stars and threaded with streams of gas. On paper, Sagittarius A star should have plenty to consume. But observation tells a different story. Much of the material that drifts near the black hole never makes it all the way in. Instead of forming a bright, dense accretion disk, the gas remains hot, thin, and turbulent. Magnetic fields twist through it, redirecting matter and pushing much of it back outward before it can cross the event horizon. In this state, Sagittarius A star exists in what scientists call a low accretion mode. It is not starving, but it is certainly not feasting. The material around it glows faintly in radio, infrared, and X-ray wavelengths, revealing temperatures of millions of degrees, yet the overall brightness remains modest. The black hole's immense gravity is undeniable, but its visible impact is restrained. Every so often, that calm is broken. Brief flares appear, sudden flashes of infrared or X-ray light that last for minutes or hours before fading away again. These events are unpredictable. They may be caused by clumps of gas spiraling inward, or by sudden rearrangements of magnetic fields near the event horizon, releasing stored energy in a violent but short-lived burst. In these moments, Sagittarius A star reminds astronomers that it is not dormant. It is simply quiet most of the time. The presence of these flares tells us something important. Even when underfed, the region just outside the event horizon is a place of extreme physics. Matter there moves at near light speed. Magnetic fields are stretched and twisted into complex shapes. Space and time are warped by gravity so intense that our everyday intuition no longer applies. Sagittarius A star may not dominate the galaxy with light, but it dominates its surroundings with curvature, shaping the motion of everything nearby. Another reason Sagittarius A star feels so elusive is its scale relative to its distance from us. Though massive, its event horizon is surprisingly small. The boundary itself spans only a few tens of millions of kilometers. From Earth, that size shrinks to an angle so tiny it is equivalent to trying to see an orange on the surface of the Moon. Imaging something that small, through layers of dust and turbulent plasma, requires precision at the absolute limits of technology. This is why, for decades, Sagittarius A star remained a black hole known by inference rather than image. Astronomers could weigh it. They could trace its influence. They could predict its behavior. But they could not see its silhouette against the background of the galaxy. To do that, they would need to combine telescopes across the planet into a single instrument and use the universe itself as part of the experiment. Only then would it become possible to glimpse the shadow cast by the monster at the center of our galaxy. To understand why imaging Sagittarius A star was such an extraordinary challenge, it helps to think about what astronomers were actually trying to see. A black hole does not glow. It does not reflect light. What can be observed instead is its effect on the space around it. As matter spirals inward, it heats up and emits radiation. Some of that light bends around the black hole, tracing curved paths through warped spacetime before escaping outward. Against this background glow, the black hole creates a dark silhouette, a region where light vanishes completely. This is what astronomers call the shadow of a black hole. The shadow is not the event horizon itself, but a slightly larger region defined by the paths that light can and cannot take near extreme gravity. Photons that pass too close are captured. Others skim the edge, looping around the black hole before escaping. The result is a bright ring surrounding a dark center, a visual imprint of gravity strong enough to trap light. For Sagittarius A star, this shadow is astonishingly small when viewed from Earth. Despite the black hole's immense mass, its distance shrinks its apparent size to a scale that defies ordinary observation. To resolve something that small, A telescope would need a resolving power equivalent to a dish the size of the planet. No single structure could ever be built at that scale. Instead, astronomers took a different approach. They linked radio telescopes scattered across the globe into a single virtual instrument, synchronized so precisely that they could act as one. This technique, known as very long baseline interferometry, relies on atomic clocks accurate to billionths of a second and enormous volumes of data recorded simultaneously at distant sites. This global collaboration became known as the Event Horizon Telescope. By observing at millimeter wavelengths, the EHT could penetrate much of the dust and plasma, obscuring the galactic center. At the same time, these short radio wavelengths offered the resolution needed to see fine detail. When signals from telescopes in Chile, Hawaii, Europe, North America, and even the South Pole were combined, the result was a virtual Earth-sized eye, capable of seeing the shadow of a black hole for the first time. Sagittarius A star, however, presented a unique complication. Unlike the black hole in the galaxy M87, which is vastly larger and evolves more slowly, Sagittarius A star changes rapidly. Material near its event horizon completes orbits in minutes rather than days. Bright regions shift position. Hot plasma swirls unpredictably. From the perspective of the Event Horizon Telescope, the target was not a static object, but a constantly changing scene. Capturing a clear image meant averaging over motion, stitching together fleeting moments into a single coherent picture. This made the data processing extraordinarily difficult. Petabytes of information were recorded, flown physically between observatories, and processed using custom algorithms designed to account for variability, noise, and uncertainty. Multiple independent teams reconstructed images from the same data to ensure that no single assumption shaped the result. Only features that appeared consistently across reconstructions were accepted as real. When the image was finally released, it showed exactly what theory predicted: a bright, uneven ring of emission surrounding a dark central region, the shadow of Sagittarius A star. Its size matched the mass inferred from stellar orbits with remarkable precision. Einstein's equations, written more than a century earlier, had passed yet another test. But the image revealed more than confirmation. The brightness of the ring was uneven, suggesting that matter on one side was moving toward us at relativistic speed, its light boosted by motion, while material on the opposite side was receding. This subtle asymmetry carried information about the black hole's spin and the orientation of its surrounding plasma. Even in its quiet state, Sagittarius A star was shaping its environment in complex, dynamic ways. What is striking is how calm the image appears, considering what it represents. This is the edge of a gravitational abyss, a place where time slows, space bends, and the known laws of physics approach their limits. And yet, the ring is delicate, almost fragile, a thin halo of light suspended around perfect darkness. It is not the image of destruction, but of balance. Matter hovering on the brink, neither falling in nor escaping completely. Seeing this shadow changed Sagittarius A star from an inferred object into a directly observed one. It anchored decades of indirect evidence to a single, powerful visual. The monster at the center of the Milky Way was no longer just a calculation. It had a shape, a scale, a presence. And still, the image tells us only about the boundary. Everything beyond the shadow remains hidden. The interior of a black hole is sealed from the rest of the universe, unreachable even in principle. No telescope, no signal, no future technology can cross that threshold and return information. Sagittarius A star can be studied only through its influence on the space around it. never through direct inspection of its core. This is part of what gives it such quiet power. The Milky Way revolves around something fundamentally unknowable, a region where our equations stop working and our descriptions fail. And yet, by watching stars drift, gas glow faintly, and light bend in delicate arcs, we can trace its outline with astonishing accuracy. We can know where it is, how massive it is, and how it shapes the galaxy, even though its true nature remains forever out of reach. When Sagittarius A star is compared to the most extreme black holes in the universe, it can seem almost modest. Its mass, though staggering by human standards, places it on the smaller end of the supermassive category. There are black holes billions of times heavier, sitting at the centers of distant galaxies, dominating their surroundings with relentless energy. One of the most famous resides in the galaxy, Messier 87, the first black hole ever imaged. That object outweighs Sagittarius A star by more than 1,000 times, yet from Earth, their shadows appear almost the same size in the sky due to the immense difference in distance. Even larger still are black holes like the one powering the quasar TAW 618, whose mass is estimated at tens of billions of suns. These objects exist on a scale that defies ordinary comparison. Their event horizons are so vast that light itself can take days to cross them. Entire solar systems could pass through without immediate consequence, drifting unnoticed until gravity gradually sealed their fate. In contrast, Sagittarius A star feels compact, contained, restrained. Yet size alone does not define influence. A black hole's behavior is shaped as much by its environment as by its mass. Sagittarius A star lives in a relatively calm spiral galaxy, where gas is spread thin and star formation near the center proceeds slowly. There is no dense river of material pouring inward, no massive accretion disk blazing across the electromagnetic spectrum. Instead, matter approaches hesitantly, heated and redirected by tangled magnetic fields, its energy dissipated before it can reach the point of no return. In more active galaxies, the story is different. Collisions between galaxies funnel enormous quantities of gas toward their centers. Starbursts erupt. Accretion disks thicken and glow. Jets launch outward, carving cavities in intergalactic space and regulating the growth of entire galaxies. In these systems, the central black hole becomes an engine of transformation. Sagittarius A star, by comparison, is an observer more than a dictator, shaping motion quietly rather than violently. Evidence suggests this was not always the case. Across the Milky Way, faint structures hint at a more energetic past. Vast lobes of gamma-ray emission extend above and below the galactic plane, known as the Fermi bubbles. These enormous features stretch tens of thousands of light-years and may be the remnants of activity from the galactic center millions of years ago. If so, Sagittarius A star may once have flared far brighter than it does today, briefly resembling a small-scale quasar before settling into its current subdued state. This idea reframes the black hole not as a fixed personality, but as a participant in long cosmic cycles. Black holes do not age or weaken in the way stars do, but their feeding habits change as their surroundings evolve. Periods of activity can be followed by long, quiet phases. 1,000,000 years of calm can be interrupted by a sudden influx of gas or a disrupted star, igniting the core once more. Sagittarius A star appears to be between such events, waiting. Its quiet nature has one important consequence. It allows astronomers to study the region around the event horizon in exquisite detail. In more violent systems, intense radiation and powerful jets obscure the subtle physics close to the black hole. Here, the faint glow reveals delicate processes that would otherwise be drowned out. Weak flares, shifting magnetic fields, and the slow circulation of hot plasma become visible clues rather than background noise. Occasionally, Sagittarius A star reminds us that this calm is not absolute. Sudden flares erupt without warning, brightening the region by orders of magnitude before fading again. These bursts may be triggered by clumps of gas plunging inward or by magnetic field lines snapping and reconnecting near the event horizon. The timing of these flares suggests they originate extremely close to the black hole, within a region only light minutes across. In those moments, the environment becomes briefly chaotic, releasing energy before settling back into quiet equilibrium. What is remarkable is how localized these events remain. Even at their brightest, the flares pose no threat to the galaxy at large. At Earth's distance, they are faint whispers rather than cosmic alarms. This reinforces a counterintuitive truth about black holes. They are not rooming destroyers. They do not actively seek out matter. Their influence is overwhelming only at close range. Beyond that, they behave like any other massive object, shaping orbits calmly and predictably. This brings us to a deeper role that Sagittarius A star plays in the Milky Way. It is not merely an object at the center. It is part of the galaxy's architecture. The motions of stars in the central bulge, the stability of the inner regions, and the long-term evolution of the galaxy are all subtly linked to its presence. Not because it dominates every interaction, but because it provides a gravitational anchor around which everything else organizes itself. In this sense, Sagittarius A star is less a monster and more a foundation. A silent mass holding the galaxy together while life unfolds far away in the spiral arms. Its influence is constant, patient, and slow, measured not in moments of destruction, but in billions of years of quiet shaping. As we continue deeper, the focus narrows once more, toward the boundary that defines the black hole itself, the invisible line beyond which no information can return. The event horizon, where time and space exchange their familiar meanings, and where the universe presents one of its most profound limits. At the heart of every black hole lies a boundary that defines its existence. This boundary is not a surface in the ordinary sense. It cannot be touched, crossed, or marked with any physical object. And yet, it is one of the most precisely defined concepts in modern physics. This boundary is known as the event horizon. For Sagittarius A star, it represents the point where gravity becomes absolute, where every possible path forward leads inward, and where the universe closes a door that can never be reopened. The event horizon is often imagined as a kind of edge, but in reality it is better understood as a region where the structure of space-time itself tilts completely inward. Outside the horizon, light can still move in multiple directions. Inside it, all paths lead toward the center. Even light, which normally travels at the fastest speed allowed by nature, can no longer escape. From the perspective of the outside universe, anything approaching this boundary appears to slow down, its light stretching and fading until it vanishes entirely. The crossing itself is never seen. The object simply slips out of the observable world. For Sagittarius A star, this boundary spans a mere few tens of millions of kilometers. That may sound immense, but compared to the scale of the Milky Way, it is astonishingly small. All 4 million solar masses of the black hole are compressed into a region smaller than the orbit of Mercury. Everything that defines the black hole's power is concentrated into this tiny volume. The rest of its influence comes from how that mass bends the universe around it. Just outside the event horizon lies one of the most extreme environments known to physics. Matter there does not orbit like planets around a star. It spirals inward, heated by friction, compressed by gravity and whipped around by magnetic fields strong enough to rival anything seen elsewhere in the galaxy. Particles move at near light speed. Time slows relative to the outside universe. Space curves so sharply that straight lines no longer exist in any meaningful sense. And yet, even here, Sagittarius A star remains restrained. The gas surrounding it is thin and chaotic, rather than dense and luminous. Instead of forming a bright, flat disk, the material swirls in a puffed-up, turbulent flow. Much of it never reaches the horizon. Magnetic fields twist through the plasma, redirecting energy outward, acting almost like a pressure valve that prevents runaway feeding. This delicate balance explains why the black hole emits so little light compared to its more active cousins. Despite this, the region is far from empty. Every so often, something disturbs the equilibrium. A clump of gas drifts too close. A magnetic loop snaps and reconnects. In these moments, energy is released in a sudden flare. For a brief time, the region brightens in infrared and X-ray light, revealing activity just outside the point of no return. These flares fade quickly, but they offer rare glimpses into processes unfolding within a few light minutes of the event horizon. The importance of this region cannot be overstated. It is here that general relativity is tested under the most extreme conditions accessible to observation. The motions of plasma, the polarization of light, and the shape of the glowing ring imaged by the Event Horizon Telescope all reflect the predictions of Einstein's equations. So far, those predictions have held. Space and time behave exactly as the theory suggests they should, even when pushed to their limits. Beyond the event horizon, however, theory alone remains. According to general relativity, anything that crosses the boundary is drawn inexorably toward a central singularity, a point of infinite density where the equations themselves break down. What actually exists there is unknown. Some theories suggest the singularity may be smoothed out by quantum effects. Others propose entirely new structures, hidden dimensions, or transitions to states of matter not yet understood. But no observation can ever confirm these ideas. The event horizon ensures that the interior of a black hole is forever sealed from the rest of the universe. This makes Sagittarius a star, a paradoxical object. It is one of the best-studied black holes in existence, and yet its core remains fundamentally unknowable. We can measure its mass with extraordinary precision. We can trace the paths of stars influenced by its gravity. We can image the shadow cast by its presence. But the true nature of what lies beyond the horizon will always remain hidden. In a sense, this is what gives Sagittarius a star, its quiet authority. It does not need to display violence or brilliance to assert its reality. Its power lies in its certainty, a region where the universe enforces a hard limit on knowledge, a place where questions can be asked but never answered directly. As our understanding deepens, the focus shifts once again outward, from the horizon itself to the tools that allowed us to approach it so closely. The instruments, techniques, and decades of observation that transformed Sagittarius A star from a faint radio source into the most intimate black hole humanity has ever studied. The story of Sagittarius A star is also a story of human patience. No single discovery revealed its nature. No moment of sudden clarity solved the mystery. Instead, understanding emerged slowly, built across generations of observers, engineers, and theorists who refined their tools and extended their reach step by step. Each advance peeled back another layer of obscurity, allowing the galactic center to come into focus without ever fully revealing itself. Radio astronomy laid the foundation. The first detections were crude by modern standards, little more than unexplained signals buried in static. But as antennas grew larger and techniques more refined, the Milky Way began to reveal an entirely new structure. Gas clouds glowed where visible light showed nothing. The galactic plane emerged as a dynamic system rather than a static backdrop. Sagittarius A stood out as a persistent source, compact and enigmatic, hinting at something unusual long before its true nature was understood. Infrared astronomy brought resolution where radio waves could only suggest. By moving to mountaintops and later into space, astronomers escaped much of the interference caused by Earth's atmosphere. Adaptive optics corrected the shimmering distortions of air, allowing stars near the galactic center to be tracked with extraordinary precision. Over years and decades, their motions traced invisible orbits, revealing mass where no light existed. Gravity itself became the measuring instrument. Space-based observatories extended this reach even further. X-ray telescopes detected sudden flares, brief moments when Sagittarius A star betrayed its activity. Infrared satellites mapped the dense star fields and warm dust near the core. Each wavelength added a new layer of understanding, like viewing the same object under different kinds of illumination. No single observation was decisive on its own, but together they formed a coherent picture. The Event Horizon Telescope marked a turning point, not because it revealed something entirely new, but because it unified everything that came before. The shadow it imaged matched the mass inferred from stellar orbits. The brightness patterns aligned with predictions about plasma motion and relativistic effects. Decades of indirect evidence converged into a single, fragile ring of light. The monster at the center of the Milky Way finally had a visible outline. Yet even now, Sagittarius A star resists complete understanding. Its behavior is subtle. Its flares are irregular. Its feeding habits remain difficult to predict. It exists in a state that feels balanced, almost contemplative, as if the galaxy has settled into a long, quiet phase around it. This calm may last for millions of years, or it may be interrupted tomorrow by a passing cloud or an unlucky star. On cosmic timescales, either outcome is equally plausible. What is certain is that Sagittarius A star will remain. Black holes do not decay. They do not burn out. They persist long after stars fade and galaxies change shape. Long after the Milky Way's spiral arms have shifted and new generations of stars have risen and fallen, the black hole at the center will still be there, quietly shaping whatever remains. In this way, Sagittarius A star is both an ending and a beginning. It marks the limit of what can be known directly, while also anchoring our understanding of how galaxies form, evolve, and endure. It reminds us that the universe is not built solely from light and spectacle, but from structure, balance, and unseen forces that operate patiently over immense spans of time. From our distant position in the galaxy's outer regions, life unfolds without awareness of the black hole at the center. Stars rise and set. Planets orbit. Civilizations emerge and vanish. And all the while, far beyond any influence we can feel, the Milky Way turns slowly around a point of perfect darkness. Sagittarius A star does not threaten. It does not call attention to itself. It simply exists. A silent presence at the heart of our galaxy, holding space and time in a quiet embrace, waiting as it always has, while the universe continues its long, unhurried journey around it. Beyond its immediate surroundings, Sagittarius A star also serves as a natural laboratory for testing the deepest ideas in physics. Nowhere else in the Milky Way do gravity, motion, magnetism, and time interact so intensely while still remaining observable. Each faint flare, each subtle distortion in starlight, And each polarized radio signal carries information about conditions that cannot be recreated on Earth. In this sense, a black hole is not only an object of fascination, but an experiment running continuously at the center of our galaxy. One of the most powerful tools in this investigation is gravitational lensing. According to general relativity, mass bends spacetime, and bent spacetime bends the path of light. Near Sagittarius, a star, this effect becomes extreme. Light from stars passing behind the black hole can be subtly redirected, stretched, or magnified. In rare alignments, a single star may appear distorted or duplicated, its light taking multiple paths around the black hole before reaching Earth. These effects are small and fleeting, but when measured precisely, they provide some of the strongest constraints on the black hole's mass and the geometry of space-time around it. Even the stars orbiting closest to Sagittarius A star become instruments in this process. As they sweep through their tight orbits, their light experiences gravitational redshift, losing energy as it climbs out of the black hole's gravitational well. Their clocks, if one could imagine them, tick more slowly near closest approach. These effects have been measured directly, offering confirmation that time itself behaves differently in strong gravitational fields. What was once abstract mathematics has become observable reality. Another layer of complexity emerges from the behavior of plasma near the event horizon. The gas, swirling around Sagittarius A star, is not neutral. It is ionized, meaning its particles carry electric charge and respond strongly to magnetic fields. These fields are dragged, twisted, and amplified by the motion of the plasma, forming tangled structures that store enormous amounts of energy. Polarized light measurements from the Event Horizon Telescope have revealed ordered patterns within this chaos, suggesting that magnetic fields play a decisive role in regulating how matter flows inward and outward. In some models, these magnetic fields act almost like scaffolding, shaping the accretion flow and preventing material from collapsing directly into the black hole. In others, they intermittently fail, releasing energy in sudden reconnection events that produce the flares observed in infrared and X-ray light. The truth may involve elements of both, a constantly shifting balance between containment and release, stability and disruption. This magnetic activity also raises questions about why Sagittarius A star lacks the prominent jets seen in many other supermassive black holes. Jets are thought to arise when strong magnetic fields channel energy along the black hole's rotation axis, launching beams of particles at near light speed. While Sagittarius A star shows hints of small-scale outflows, it does not produce the dramatic, galaxy-spanning jets seen elsewhere. This may be due to its relatively low feeding rate, its spin, or the geometry of its magnetic fields. Or it may be a temporary condition, one that could change if the environment around it evolves. Looking farther outward, the influence of Sagittarius A star blends into the broader dynamics of the galactic center. The central region of the Milky Way is crowded and restless. Star formation occurs in bursts. Massive stars live fast and die young, shedding material into space through winds and supernova explosions. Some of that material drifts inward, joining the complex circulation of gas near the black hole. Some is pushed back outward by radiation and magnetic pressure. Over millions of years, this exchange shapes the density and structure of the inner galaxy. There is also growing evidence that Sagittarius A star has interacted with its environment more dramatically in the past. X-ray echoes detected in nearby gas clouds suggest that the black hole was significantly brighter a few hundred years ago. These clouds appear to be reflecting ancient bursts of radiation, delayed by the time it took light to travel outward and back toward Earth. If true, this means Sagittarius A star has already demonstrated its capacity to shift between quiet and active states, even within the relatively short span of recorded human history. Such variability reinforces the idea that black holes are not static monuments. They are responsive systems, deeply connected to their surroundings. Changes in gas supply, stellar dynamics, or magnetic structure can alter their behavior on timescales ranging from hours to millions of years. Sagittarius A star may appear calm now, but calm in cosmic terms does not imply permanence. As observational technology continues to improve, astronomers are beginning to watch the galactic center with unprecedented continuity. Networks of telescopes monitor Sagittarius A star across multiple wavelengths simultaneously, ready to capture the next unexpected flare or subtle shift in behavior. Future upgrades to the Event Horizon telescope promise sharper images, and even the possibility of tracking motion near the event horizon over time, creating a kind of slow-motion view of spacetime in action. In this way, Sagittarius A star remains unfinished as a story. Each observation answers one question while raising several more. Each improvement in resolution reveals new complexity rather than closure. The black hole at the center of the Milky Way is not a solved mystery, but an ongoing conversation between theory, observation, and the limits of what can be known. When all of this is taken together, Sagittarius A star stops feeling like a distant astronomical object and begins to feel like part of the architecture of reality itself. It is not merely something that exists in the Milky Way. It is something the Milky Way is built around. Long before the sun formed, before Earth cooled, before life found its footing, this black hole was already there, shaping the motions of stars that would never know its name. From our position far out in the spiral arms, the galaxy feels stable, predictable, familiar. Night after night, the stars appear to hold their places. But at the center, something profoundly different exists. A region where time slows, where space curves back on itself, and where the future has fewer options than the past. Sagittarius A star is a reminder that stability and extremity are not opposites. They can coexist quietly, layered on top of one another across vast distances. What makes this black hole especially remarkable is not its violence, but its restraint. In a universe filled with explosions, collisions, and blazing energy, the most powerful object in our galaxy spends most of its existence in silence. It does not need spectacle to assert its role. Its presence is written into the orbits of stars, the shape of the galactic bulge, and the slow rotation of the Milky Way itself. There is also a strange comfort in its distance. Though unimaginably massive, Sagittarius A star poses no threat to life on Earth. Its gravity does not reach us in any meaningful way. Its occasional flares fade long before they arrive. The monster at the center of the galaxy is not a looming danger, but a quiet constant, far removed from the rhythms of human time. In that separation, the universe offers perspective. Enormous forces can exist without disruption. Power does not always announce itself. As technology advances, our view of Sagittarius A star will continue to sharpen. Images will become clearer, measurements more precise, models more refined. And yet, no matter how far observation progresses, there will always be a boundary we cannot cross. The event horizon remains an absolute limit, a place where information ends and speculation begins. This is not a failure of science, but a feature of the universe itself, a reminder that knowledge has edges. In the end, Sagittarius A star stands as both an answer and a question. It confirms theories written generations ago, validating our understanding of gravity and spacetime. At the same time, it points toward mysteries that remain unresolved, about the nature of singularities, the union of gravity and quantum physics, and the ultimate structure of reality. It invites curiosity without promising closure. And so the Milky Way continues its slow rotation, stars tracing their paths around an unseen center. Civilizations rise and fall on distant planets, unaware of the dark anchor holding their galaxy together. Time moves forward, quietly, patiently, while Sagittarius A star remains where it has always been. Silent, massive, unmoving. At the center of everything we call home, there is darkness. Not empty darkness, but a presence so dense that it bends the universe around it. And in that quiet center, the galaxy finds its balance.